Yeah, welcome. So in this lecture, we will be discussing the implementation details of AVL trees. Okay. So we'll be discussing like how to implement AVL tree using C programming, and also basically we'll be discussing how to insert a node into an AVL tree, and how to, and if the tree got unbalanced, then how to balance it, right? And also we'll be discussing like how to identify the balance factor of a particular subtree or a particular node, and also we'll be discussing how to find the height of a tree, okay, or height of a node, right? These are the key things which we'll be discussing, right? So the main important things are how insertion will be done. The logic for insertion is same as that of binary search tree, there is no difference, but after insertion we have to check the balance factor for every node, and we should ensure that the balance factors are not less than -1 or not greater than 1. That is, it should be in between -1 and +1, including minus 1 and +1 are also acceptable. Okay. If that is not the case, then we have to rotate. Okay. So, so whatever we have discussed in theory, that we will be discussing how to code. Okay. So the important thing to include in the coding is how will you find the height of a particular node, how will you find the balance factor of a node, and how will you perform the rotations. Okay, these three are the core things. Fine, so let us start. So here we are including the header files as usual, stdio.h and stdlib.h, and this is the node definition, struct node int key, and there are two pointers, left child and right child. We are introducing one more parameter in the node definition, that is height. Every node will include a parameter called height. Okay, when a new node is created, its height will be 1. Okay, when we create a new node, its height will be 1. Okay, and also when we create a new node, we will update that parent's height as we should update the that particular node's parent's height. Okay, now how should we update that? See, this actually you should have the clarity. Whenever a node is created, for that new node we will set the height as 1. Okay, now how will we update the height of its parent? Okay, so we cannot add directly 1 to the parent site. Okay, that cannot be done. Okay, so so what should we do then? Okay, so that's what I'll give you a brief on that. uh, it's, so it's nothing great. Only thing what you have to check is, after adding a new node, you have to go to its parent node. Okay, you have to go to its parent node and check like what is the height of the left subtree of the parent, and also you have to check what is the height of the right subtree of the parent. Okay, right? So both things, two things you have to check. Say the tree is, we don't know how much lengthy the tree, or what is the length of the tree, all those things we don't know. Okay, say one particular node, after, say there is a node x, after that node you have inserted another node y. Okay, either as a left child or a right child. Now whether, say we have inserted y as a right child, whether x as a left child or not, and how long this all this history we don't know. Okay, so what is the parent of the x, and where is the root node, that we don't know. Okay, but there is somewhere the root node is there, and how many childs are there for x, which is the parent of the new node, that also we don't know. Okay, then how should we update the height? So this is the new node. So this new node's height will be, we will, whenever we create a new node, we will set its height as 1. That is fine. Up to that it is fine. Okay. Then its parent node, we have assume we have access to its parent node. How to access the parent node, that I will be letting you know. Okay. Time being, assume that we have access to its parent node. If you have access to its parent node, then how to update its height means, you have to find the height of its child its left child and its right child. Okay, its right child height we know because whenever you add a node, that will be added as a leaf node. Okay, so its right child's height is 1. Okay, its left child height we don't know. Let us assume it is h1. Let us or hl. The height of left child is hl. Okay, now you take these two things. Okay, or even this height of right child also we can call as hr. Okay, hr is the height of the right child. Okay, whatever the right child, right? Now you take these two and you find max of hl and hr. Max of hl and hr. Okay, that is the highest of hl and hr. Okay, that we find out, and to that you add 1. That's it. This is how we are going to update the height. So this logic will work, right? Say if you have added the new node to the right, then obviously left child's height will be more. Okay, let us assume left child height is 3. So in that case hl is 3, hr is 1. Okay, so max of 3 comma 1 is 3, but this is what height of the left child. Okay, and this is in another level, so x height will be plus 1 to that, so that we are adding plus 1, right? This process should be continued until you reach the root node. So this is x. Okay, then go to the parent of x. Okay, assume that we have access to the parent. How to access that I'll let you know. Okay, so say this is x minus 1. Okay, this may be a left child or a right child, and how much its length, all those we don't know. Again apply the same logic. Okay, for this particular node, now previously we have found the height of the left child of x and the height of the right child of x. Now you have to find the height of the left child of x minus 1 and the height of the right child of x minus 1. Whatever the maximum, take that and add 1. Continue this process until you reach the root node. Okay, this is the logic. This is how we are going to what you call update the height, right? Okay, now you may ask, like, how do we access the parent node? Okay, say for example I'm drawing a particular binary search tree, say 5 3. Okay, 2, right? And here is 4. Okay, 4 is greater than 3 and less than 5. Okay, and here is 7 8 and 6. This is a binary search tree. Okay, every node's right is greater than that node and every node's left is less than that node, right? Okay, say for example up to this the height is known, let us assume, right? So what is the height of this particular node? It is 1. It is 1. For all leaf nodes height is 1, right? 1 1 1. Okay, what is the height of node 3? It is max of its left child and the right child plus 1. So both the left child and right child are 1 only. So anything you can take. Okay, both are equal, right? So it is 1 1 plus 1 is 2. So this is also 2. Okay, again if you see the height of this particular node 5, it is max of its left child and its right child. Both are same. So it is anything you can take, either this 2 or this 2. 2 plus 1 is 3. Fine. Say now I want to add another node. Say the new node we want to add, let us assume the node 9 I want to add. Okay, now how to update the height, that let us discuss. Okay, so where to add 9, you follow the normal binary search technique. Starting with the root node, we have a pointer to the root node, so check whether 9 is greater than this root node or not. Okay, so we have another pointer traverse also, which is also pointing wherever root is pointing. Okay, so check whether 9 is greater than 5 or not. Yes, 9 is greater than 5. In that case, what you do, you just push that 5 into stack, that is node 5 into stack. I'm calling it as n5. Okay, or a pointer to n5. Okay, not that we are not pushing the node itself, a pointer to node 5 is pushed into stack, and then move to the right. So now traverse is not pointing here, traverse is pointing here. Traverse is pointing to node 7. Okay, again check whether 9 is greater than 7 or less than 7. It's greater than 7, so once again you have to move right. Okay, so before moving right, push the current traverse wherever traverse is pointing, that pointer into stack, So a pointer to node 7 is pushed into stack. So now traverse is pointing to here, node 8. Again check whether 8 is greater than 9 is greater than 8 or not. Yes. So once again push this into stack. There is node a pointer to node 8 is now pushed into stack. Okay. Now traverse is not pointing here. Traverse is pointing to null. Okay. So how long you should do until traverse becomes null you have to do. Okay. We maintain one more pointer also previous. The logic is as usual how we discussed in what you call in binary search tree. So whenever traverse is move when traverse move to 7 previous will be pointing to 5. When traverse move to 8 previous will be pointing to 7. When traverse move to null previous will be pointing to 8. Okay, previous will be pointing to 8. Now this is the location we want to insert the new node, but we don't know where we have to insert, whether it be left or right. So you check whether 9 is greater than wherever previous is pointing or not. Yes, it is greater than the key value of previous, because the key value of previous is 8. So as 9 is greater than 8, 9 should be added as a left child, a right child. If it is less than, then you have to add as a left child. So 9 will come here, right? 9 comes here. Fine. Now what you do? Now for the new node we know the height. Its height will be 1. Okay. Fine. Now what you do after adding this, you pop this n8. So when you pop n8, you get a pointer to the parent. Okay. Let us say that we popped the top from the stack and we are keeping it in a pointer called parent. Okay. So now parent is pointing to 8. Now parent is pointing to 8. Okay. Now check the height of the left child of parent and the right child of the parent. Okay. There is no left child for parent. Okay. So that height is 0. And the right child height is 1. Okay. Take the max of that. Max of this 0, 1 is 1. And then add 1 to that. Okay. So when you add 1 to that, 2. So that is the height of this node. Okay. Again you pop. How long you should pop? Until stack becomes empty you have to pop. Now pop the second next. So this now top of the stack is n7. Okay. Now parent is pointing to the node 7. Okay. Again check what is the height of the left child of node 7. Left child is 6. So that height is 1. And what is the height of the right child of node 7? That is just now we updated, that is 2. Okay. The max of 1, 2 is 2. And to that you add 1. 2 plus 1 is 3. So that will be the height of node 7. Okay. Is stack is empty? No. So push, now the top of the stack is n5. Now push n5 to stack. Okay. Now parent is not pointing here. Parent is pointing to node 5. Okay. Again you check what is the height of the left child of parent. Parent is node 5. Node 5's left child height is 2. And what is the height of the node 5's right child? It is 3. The one which is recently updated, 3. And what is the max of this? Max of this is 3. So to this add 1. So the new height of node 5 will be 4. Okay. Okay. This is how we update height. This is the logic to update the height. Okay. So with this understanding, let us see the code. Okay. So we have introduced a new variable called height here. And as usual, we are creating a pointer called root, and currently it is pointing to null. And we are going to maintain a stack, and this stack is a this stack will be holding the pointers. Okay, whatever the stack I have shown, it is a pointer. It is going to hold the pointers. Okay, so here I am creating an array of pointers. I'm creating an array. The array can hold 100 elements. But each of these 100 element will be a pointer. Okay. I thought of using another pointer, sp stack pointer, but I don't think I'm using it. So this is something like a dummy, right? And stack top initially set to -1, size is 100. Okay. And there is a function insert. So this is just a declaration of that function insert, which is to insert a new node to the AVL tree, right? So this is the logic for pushing a node into the stack. Okay, this is self-explanatory. You can go through and you can understand it because we have discussed several times stack. Okay, and this is the function to pop a node out of the stack. Okay, again you can go through this, right? and this is the function to which will return the height of a particular node. Okay, so its return type is integer. The function name is height. It takes one argument which is a pointer to a node, and it checks whether the pointer is null or not. If the pointer is null, it returns 0. So why should we check this condition for null? In the sense, for example, if you have recollect from here, see, if you take this node 8, it does not have a left child. So in that case, its left child is what? Null. Okay. So you can just call, for example, when parent is pointing to 8, if you want to know the height of its left child, you can just call the function height. Height of, you can just call the function height, height of a parent arrow left. But there is no parent arrow left. Parent arrow left is null. Okay. No, in the sense actually it is null. Okay. So we are pausing null. But when you pause null, also this function will return 0. Okay, when you pause null, this function will return 0. That is, if whatever the node you are pausing is a null, okay, there is nothing, so it returns 0, right? So that our calculation will become easy. When you pause right, there is a node, okay, so it will return that node's height. If it is not null, it will return that node's height, okay. And then there is a function to calculate the balance factor of a node. So this function also returns an integer, and the function name is balance factor. It takes a node as a pointer to a node as an argument. See here, it's a very nice code. We are using something like this: return height of n arrow left child. So this height of n arrow left child will tell the height of the left child using this function. Similarly, height of n arrow right child will give the height of the right child by calling this height function, and then subtract that, whatever the height of left child minus right child. So that is balance factor, right? And create AVL tree, the function, it's very similar to that of create BST, binary search tree. In fact, I have used the same code. Okay, for your information, I have used the same code which we have used for BST. Only instead of BST here, I changed the name as AVL. Okay. So anyway, I'll give a brief intro. So some pointers we are declaring traverse and previous as usual, and then some local variables we are using n, k, and I. We are asking the user to enter the number of nodes in the AVL. It should be AVL. Okay. So AVL tree, and okay, then user gives the number of nodes, and then we first we create memory for one particular node, right? We are not creating memory for all the nodes. Okay, so whenever we create a new node, then we allocate memory. Okay, so first we create memory for one node, so that node will be pointed by the root pointer. Okay, and then we are asking the user to enter the key for the root node, and we read that. Okay, so root node's key will be that k, whatever the key we read, and currently this is the first node. So root's left child is null, root's right child is null, and root's height is 1 because this is the first child. Okay, then we are running a for loop for I is equal to 2, I less than or equal to n, I plus plus, because one child you have created, one root node you have created. Then we are asking the user to enter the key for the next node. We are reading that key, and then we are inserting this new node through the insert function. Okay, we are not what you call, we are not writing the code here itself directly, rather we call the insert function which will insert, and for that this key is paused. Okay, so if you come to the insert function here, so the insert function is the one which inserts the node. Okay, so here is the insert function. Here there are many pointers: traverse, node, previous, parent, closest, and there is another PAR, because I'm using for two places. Okay, so I'll let you know what all these things are. Okay, and then there is a variable BF which is used to temporarily hold the balance factor. Initially traverse is pointing to root, that is the first node. Okay, so we want to insert, so first we check, this is same BST logic, while traverse not equal to null, so this is the node which you want to insert. If S1 here itself we are checking, we are not using that search function here. Whatever the node you want to insert, here I am checking if that node is equal to traverse arrow key, that is already available in the tree. If it is already available, then we say that the node with the key already exists and we exit. Okay, otherwise, else else if this is the new node which we want to insert, the new node we read there as k, here it is received as s1. If s1 is less than traverse arrow key, then traverse should move to traverse arrow left child. Okay, traverse should move to the left child. But before moving that, we are tracking the previous node in the previous pointer. So we are doing previous equal to traverse and then traverse equal to traverse arrow left child. Else, if this is not satisfied, then it means that s1 is greater than traverse arrow key. In that case, it should go to the right child. So previous equal to traverse and traverse equal to traverse arrow right child. Okay. Meanwhile, what we are doing, every node we are pushing. The previous node we are pushing into stack. Okay. Why we are pushing? Because we should update the height. Okay. So recall that updating the height, we should, whenever you insert a new node, whatever the path you are traveling to insert the new node, all those nodes should be pushed into the stack, because all those nodes height should be updated. So we are pushing that node into stack. Okay. So this while loop repeats until traverse is what you call it becomes null. Finally, when at one point when traverse become null, previous will pointing to that particular node, after which the new node should be inserted. Okay, right? Then we allocate space for the new node. So node is the pointer which points to the new node, and that node's key is set to s1, and that node's left child and right child are set to null. Okay, and this new node's height is set to 1, because new node's height will be always 1. Okay, but now we should yeah, okay, and then where this new node should be added, this is, we have just created the new node. New node should be added after previous, either it should come as a left child or as a right child. Okay, so if new node's key, that is s1, if it is less than the key of previous, then new node will come as the left child of previous. Okay, otherwise new node will come as a right child of previous. Okay, so with this, insertion is done successfully. Okay, if you see, the code is same as that of BST. Only thing, we are pushing all these nodes to the stack. After every iteration, these nodes are pushed into the stack. Okay, now we have to update the height. Okay, so this parent pointer, now here we are using parent equal to pop. So whatever the recent parent of the newly inserted node, that will be popped out, and I'm passing it to the, and we are passing this to the function update height of parent. Okay, update height of parent. If you see, stack is declared as a global variable, so stack can be accessed from any function. Okay, it is not that stack has to be accessed only from here. Okay, it can be accessed from any function, because stack is declared as a global variable, right? So what I'm doing here is just, what we are doing here is just, we are taking the first item of the out of the stack. Okay, that is whatever the immediate parent of the newly inserted node, and that is being passed to update height function. uh, okay, so let me show you the function update height. It's very simple. Okay, here it receives so the update height function, it passes the parent node, and that is received in another local variable parent. Okay, and we are checking whether parent is not equal to null. If parent is not equal to null, then parent arrow height is equal to same whatever we have discussed, max of height of parent arrow left child comma height of parent arrow right child plus 1. See, max is another function which will just return max of two numbers. Okay, it's a very simple function. It returns an integer. It takes two integer arguments a and b. It checks whether a greater than b or not. If a greater than b, it returns a, otherwise it returns b. Okay, so this function is we are using this here. Okay, so we are using this here, so it just checks what is max. If max is whichever the out of these two things, whichever the max, it takes it and add 1 to that, right? So this is how the immediate parent's height is updated. Then once again we give parent equal to pop, so the next element will come out. The first thing we updated is the parent. Next we are updating grandparent. Like that we keep updating until parent becomes null. Until parent becomes null. Okay, so okay, so basically this function update height, it will update the height for all the nodes, starting from the parent to grandparent up to the root node. It will update the height. Okay, So after inserting every node, you have to update the height. Okay, fine, right? Then what should we do? After updating the height, this will just update the height. But after updating the height, the tree may get unbalanced. Okay, so if the tree is unbalanced, that also we have to check whether the tree is unbalanced or not. Okay, so again we start searching for all the nodes. Is there any node got unbalanced? So once again we are setting traverse to root. So traverse is pointing to the root node, previous is pointing to null, while traverse not equal to null. Okay, we check the balance factor of traverse. Currently traverse is pointing to the root node. What is the balance factor? We are taking it. I'm giving this print just for verification, it's not required. Then we check whether the balance factor, this is currently root node, this is the first node, whether the balance factor is less than -1 or greater than 1. If it is less than -1 or greater than 1, then something wrong, the tree is unbalanced. Okay, so then we are noting down that pointer. What pointer? uh, Parent is equal to, we are saying parent is equal to previous. Okay, previously you see previous is null. Okay, now parent becomes null, and closest is equal to traverse. Okay, that is currently the root node is the closest. So what is this closest, you may ask? Okay, what is this closest, you may ask? To give clarity, I'll just show you one graph. Probably that will give the clarity of that. Sorry, I'll show you one tree. Okay, where is that? Just a minute. Okay, so say this particular tree, this particular this yeah, this particular tree. Okay, this particular piece of tree, if you see, there are two nodes which got in unbalanced. One is node 13, another one is node 10. Okay, so we say after inserting node 7, after inserting node 7, some rotation was done, something was done. Let us ignore that. Okay, just understand that after inserting node 7, two nodes got, or say take this also, this is also fine. After inserting node 7, two nodes got unbalanced, node 13 and 10. Okay, now from which node we should start our rotation process? Is it from 13 or 10? That might be your question. Okay, so you have to choose the node which is closest to the newly inserted node. Okay, so that is when you go from 7, which is closest. 7 is the newly inserted node, so 7 is inserted along this way. 7 is inserted as a right child of 6, which is a right child of 5. Okay, and 5 is a left child of 10, and 10 is the one which is closest to 7. Okay, so we should start what you call rotating. Our reference should be node 10, not 13. Okay, are you getting? So what we are trying to do there is we are trying to find the closest node which got imbalanced. It is not just the node which got imbalanced, the closest node which got imbalanced, so that we are looping around. Okay, so but we are now coming from top to bottom, not from bottom to top. That is, from node 7 you cannot go to node 13 because we don't have a pointer to point to the parent. So from 13 only we have to come to 7. We know that already we inserted 7. So where 7 will be inserted, that we know. As 7 is less than 13, it should be here. Okay, so we start with 13. We check what is its balance factor. It is less than see here here actually they are calculating balance factor as right child minus left child, height of right child minus left child, so that it is coming as -2. In our case we are following height of left child minus right child. Either way you can do. Okay, so we will get +2, so ignore this also. So in our case we'll get a +2, but it is a unbalanced one, right? So when you see 13, 13 is unbalanced. So initially we set this is the closest node which is unbalanced. But again when you come to 10, 7 is less than 13, so you have to go left. Again when you see 10 is also unbalanced. So now we set 10 as the closest node which is unbalanced. Okay. Then we go to 5. 5 is balanced, so we will not change the closest pointer. Then we go to 6. 6 is balanced, so we will not change the closest pointer. Then we go to 7. 7 is the one which we recently inserted, so we come out. Okay, So along the path from root to 7, there are two nodes which got imbalanced, but the closest one is 10. So we need to find the one which is closest to the newly inserted node, right? So that we are maintaining this closest point. Okay. So whenever you find a node which is imbalanced, we set that the previous of that node will be called as the parent. Okay, PAR, because already we are using a parent pointer, so I'm not using that same pointer, rather PAR. And whatever the node which is uh, got imbalanced, that will be called as closest. So in this case, traverse is the one which got imbalanced, so closest will refer to that, right? Okay. Then we check whatever the currently traverse is, that is equal to key or not. If it is equal to key, break. Otherwise, you check whether it is less than, whether the current S1 is nothing but the key of the newly inserted node, whether it is less than traverse arrow key or not. In that case, we have to move to the left child. But before moving to the left child, we are also storing the previous pointer in traverse. That is the parent in, sorry, previous pointer in previous. That is, parent is stored in previous and then traverse is updated. If S1 is greater than key of traverse, then traverse should point to right child. Again, in this case also we are storing current traverse in previous and traverse got updated. Okay. So like this the loop continues. Okay. So another in the, so it continues for all the node until it reaches the particular node which is newly inserted. Meanwhile, if there is some other node, if it finds that also got unbalanced, then that node will be stored in closest and that node's parent will be in PAR. Okay. So the point is we want to find the node uh, from the newly inserted node which is the closest one from the newly inserted node which got unbalanced. Okay. So this loop will do that. This loop will do that. Okay. And this while loop will take care of that. And another important thing, one, if assume that there is no, because of the insertion, none of the node got unbalanced. If none of the node got unbalanced, then this loop will not at all execute. Okay. I mean, this if condition will never satisfy. The while loop will execute, but this part will never execute. Okay. If none of the node got unbalanced, then this part, this if condition will never execute. If that is the case, then closest will be null. So after coming out, we check whether closest is null or not. If closest is null, then we say that the insertion has not created any imbalance and we return from this function because nothing to do. Okay. If closest is not null, then only this part will execute. Okay. If closest is not null, then what is the case? Then there is a imbalance. Now if there is a imbalance, then you have to rotate. So we know that there are 4 types of rotation: left rotate, right rotate, left and rotate, and right and left rotate. Okay. So how to do that? How to identify what type of rotation is to be done? Okay. So for that, there is nothing difficult in that. Okay, it's actually an easy concept. So for example, assume that we want to perform a left rotation. So when you want to perform a left rotation, you know the node which got unbalanced. So A is the node, or in our case, that is getting pointed by the pointer called, as what? It is getting point closest. So in our case, closest is A. Okay. Closest is A. Okay. And you just check what is the value in closest. I mean, what is the branch factor of closest? It is a positive number. If the closest, I mean, it is a positive number and it is greater than 1 because it got unbalanced. Okay. So if the closest node's balance factor is greater than 1, okay, and if the left child of that node, and if the left child of that node's balance factor is greater than 0, okay, then it means that it is a LL thing. It is a LL thing. In that case, you have to perform a right rotation. In that case, you have to perform a right rotation. Okay, so in this case, actually we have to perform a right rotation. Okay, so yeah, so that how we will check here. So that's what here we are checking. Okay, if balance factor of closest is the node on which imbalance is created. Okay, in this case closest is A, right? If that is greater than 1, okay, it is 2, right? And balance factor of closest arrow left child, okay, that is this B, which is greater than 0. Both are positive. Okay, it's left, this is also positive, this is also positive. In that case you have to perform right rotate right closest, and that on closest you have to perform right rotation. For the right rotate we are passing that parent pointer also. Okay, how the rotation does that we will see later. So there is a function rotate right. Okay, similarly how left rotation is done, let us see here. In left rotation it is just the reverse of that. You see, the node on which imbalance created, that becomes a negative number, that is less than -1, and the right of that node is -1, that is greater than, it is less than 0. Okay, so that is what we are going to check here. uh, if if balance factor of closest is less than -1 and balance factor of closest arrow right child, okay, now it's right child, is less than 0, in that case rotate left, again pause closest and parent. Okay, fine. Then if it is right left case, okay, if it is right left case, then in case of left right rotation, what happens in the sense, the logic is same, even though in the class we have discussed 3 cases, but for all the cases the logic is same. Okay, here what happens, say this A is the node which got imbalanced. Okay, so that has a positive number, but its left child, it is imbalanced, and it is having a positive number, that is it is having a number greater than 1, and its left child has a negative number which is greater than 0. In that case you can confirm that it is a left right kind of rotation. Okay, so what we check here, if balance factor of closest is greater than 1, which is the one which got imbalanced, and balance factor of closest arrow left child is less than 0, then you have to perform a left rotation and a right rotation. Left rotation on what? That is an important question. Left rotation on B. B is what? B is, this is closest. B is closest left child. B is closest left child. So left rotation on the left child of closest. And what is its parent? B's parent is A. So this node's parent is closest. Okay. So how do we write that code? Rotate left closest arrow left child. That is, now rotate on the left child of closest, and that child's parent is closest. Okay, this print is just for checking. Okay, so this is the first rotation. Once you did that rotation successfully, then you have to rotate on the node which got imbalanced. So there you have to perform the right rotation on this particular node. Okay, and we don't know whether it has a previous node or not. If it does not have a previous node, that will be null. Okay, uh, but it may happen in some intermediate level also, right? So that we are using that previous for the parent. Then rotate right on closest with its parent. Okay, right. So then the last case is uh, right rotate and right left rotation. Okay, so which is just the reverse of left right rotation. That is, if the one which got imbalanced is less than -1 and its right child is greater than 0, then you have to first perform right rotation and then left rotation. Right rotation on the right child of the closest with closest as the parent, and left rotation on closest with parent. Okay, sometimes this parent may be null. Okay, so that in the rotation part we will take care. So once this rotation were done, the once any one of the rotation is done, okay, we have to identify the correct rotation and do that. Once it is done, the tree will be balanced. So we say that insertion created imbalance, and the AVL tree was balanced again. Like that we will say a print. Okay, so this is how we do insertion. Now we'll let us see the code for left rotate and right rotate, which is an important thing. First let us see left rotate left. Okay, so if you see rotate left, I'll take that. Anyway, these are the two rotations we are going to do, nothing more than that. Okay, so this is for left rotate. Okay, if it is left rotate, what will happen? So the node on which you are going to perform the left rotate, okay, that node's right child, will become the root. Okay, that node's right child will become the root. We don't know whether this has any parent or not. Sometimes this may have parent. Okay, assume that A is a child of some other node. Okay, then we don't know whether A is a left child of this node or A is the right child of that node. It may be either left child or it may be a right child. Okay, if A is the left child of that particular node, then now B will become the left child of that node. Okay, if A is the right child, then B will become the right child. Okay, so first you have to check. How do we check that? If A is less than that particular node, that is if the key value of A is less than that parent's node, then surely A will be its left child. Then B will come as its left child. If A is greater than that particular nodes, the parent node or its key value, then A is the right child, then B will come as a right child. Okay, that is the first move we will do. Okay, then where A will go, A will become the left child of B. Okay, this B is left child, A will become B's left child. Okay, and what will happen to this BL? BL will become the right child of A. That's all. So these are the three movements which you have to make. Okay, the first movement is required only if there is a parent for A. If there is no parent, then you need not do that. Okay, so first what we do, A is the node on which the imbalance is created and P is the parent of A. Okay, then we create another node B. There is another pointer we create, and B is going to point where? B is going to point to the right child of A. Okay, the right child of A is nothing but B. So that same name I have given. With this logic only I connected the code. Okay, so the one we want to rotate is A and its right child is B. Okay, fine. Then if we check whether P is not equal to null. What is P? P is A's parent. If that is not equal to null, then we have to see whether B will become its left child or its right child. Okay, again you check if parent's key is greater than A's key, then if parent key is greater than A's key, then it means that A will be the left child. In that case, now B will become the left child. So parent's left child will be B. Otherwise, parent's right child will be B. Okay. So with this, what we have done, we have effectively made B as the root of the tree. Okay. Now A should become the left child of B. Okay. Right. And also A's right child should be B's left child. Okay. So first we are writing A's right child is equal to B's left child. That is whatever B's left child. See this from right to left. Whatever B's left child. What is B's left child? BL. That BL will become now A's right child. Okay. So that will become A's right child. Okay. Fine. And what will be B's left child? B is the root now. So B's left child will be A. And B's left child is equal to A. Okay. Right. Fine. Right. Now say for example there is no parent. If there is no parent, in this case if there is no parent, then previously A is the root. Now which is the root of the tree? Now B has become the root of the tree. Okay, so you have to check which is the root, because when you want to traverse, we always traverse starting from the root. Okay, otherwise this will create a problem. Otherwise your root is now pointing to B. Okay, your root is still pointing to A. Okay, so we are checking whether A is a root node or not. If A is a root node, then we are changing root equal to B. Okay, then we adjust the height of both A and B. These are the two nodes which we have modified. So you adjust the height of both. A arrow height is equal to, as per our logic, max of height of A's left child comma A's right child plus 1. B's height is equal to max of height of B's left child comma B's right child plus 1. Okay, if parent is not equal to null, then update the parent's height also. Parent height also will change, right? So these are the updations which we are doing. Okay, fine. So this is for left rotate. Similarly for right rotate also, this is the code. Okay, so in right rotate, if you see so this is, so yeah, in right rotate, yeah, in this case this is A, yeah, again this is A and this is B. So first, so A's left child is B. Okay, so the parameters are same. A is the one which you want to rotate and P is the parent of A. Then B is nothing but A's left child. B is nothing but A's left child. Okay, and where now B will become the root. B will become the root. But if A has a parent, then B should become either that parent's left child or right child. So that logic is same. That logic is same like how we discussed for left rotation. If P not equal to null, then we check whether P's key is greater than A's key. If P's key is greater than A's key, then A is the left child of P. Then B also will be the left child of P. Otherwise, B will be the right child of B. Okay. So with this, B has become the root. B has become the root, but still root is not pointing to B. Okay. Here itself, if you want, you can write root equal to B. But we are not doing that. Let us see what to do. Okay. Then A should become what? A should become B's right child. Okay. And previously, whatever B is right, that should become A's left child. Okay. So first we do that. That is A's left child will be B's right child. So B's right child, see from here, what is B's right child? B's right child is this, that is assigned to A's left child. Okay. So A's left child will be B's right child. And what will be now B's right child? Now B's right child will be A. And then we check whether A is the root of the tree. A's root of the tree is in that case, then now the root will become B. Right. Again we update the height for A and B. And if P is not null, then we update the height for P also. Okay. So this is how we perform the left and right rotation. Okay. So that's the logic. Okay. I think we have discussed the entire thing, and finally this is the main function. And here I'm using a variable ch equal to 1, which is to insert new nodes into the AVL tree. I'll show you in the execution. Create AVL, which is used to create an AVL tree with certain number of nodes. Then after creating node with some 10 nodes, then if you want to insert one more node, it will ask. Then if it is 1, it will allow you to insert. If you give 0, it will not allow you to insert. Okay. If it is 1, if ch is not equal to 0, it means it is 1. Then it will ask the user to enter the key of the node. Okay. Then we read the key using scanf. Then we insert it. Okay. This insertion itself will take care whether the tree got imbalanced or not. If it is imbalanced, it will balance, and then it will display in order format. Then again it asks one more node you want to insert or not. Like that it proceeds. Okay. So let me execute the code and show you the output. Compiling. Clear the screen. Okay. So it's asking enter the number of nodes. I'll give as 8. Okay. So here is a tree I'm having. So based on this I'll give the input. Okay. So for example, this tree I will take. Okay. So currently if you see, this has how many nodes? It has 1 2 3 4 5 6 7 8. Okay. So as per this I'll be giving the input. So it has 1 2 3 4 5 1 2 3 4 5 6 7 8 nodes. Okay. So the first node is 13, then 10, 15. Okay, it's inserting. There are some unnecessary printfs are there, ignore that. Okay, 5, 11. So first 8 nodes it will insert without asking anything. Okay, because we have given initially there are 8 nodes. Okay, 16. If there is any imbalance, it is telling here. Okay, it is telling, you can see that the insertion has not created any imbalance. So far it has not created any imbalance. Okay, because we are inserting in that particular order. 4, no imbalance. 6, no imbalance. Okay, right. Now it is asking, do you want to insert one more node? Yes, I want to insert. So let us say I want to insert this node 14. So I am saying first 1, that is I want to insert, then 14. This also is not creating any imbalance. So here the balance factor of all the node is displayed. You can see none of the balance factor is either less than -1 or greater than 0. That's fine. Okay. Now let us come down. Now we are inserting a node 3. When you insert a node 3, it should create an imbalance. Okay. So sorry. So now again it is asking, do you want to insert one more node? Yes. Node 3. So it is saying insertion created imbalance and the AVL tree was balanced. Okay. So this is after balancing. After balancing, here you can see 13 is -1 and 4 is -1. So because they are considering right tree minus left tree. Okay. The height of right subtree minus the height of left subtree. So it is -1 they are getting. We are taking as height of left subtree minus right subtree. So it should be reverse of that. We should have +1 in 13 and plus 1 in 4, remaining all should be 0. So you can see here, for the node with key is 4, the balance factor is 1, and for the node with key is 13, balance factor is 1. Okay, right. Again, say let me try to insert one more node, say the node 7. Here also you can see the insertion created imbalance, and the later the t got balanced. Okay, so like that you can keep inserting any nodes. This logic will work, right? So this is how we create what you call uh, uh, AVL trees, and we can perform insertion and rotations, all those things. Okay, searching is very similar to that of binary search tree. So I have not implemented the logic here. Actually the function is there, I have not used it. You can use that. And then what else? And removing the node, deleting a node is also, the logic for deleting the node is also same as that of binary search tree. Okay, that is, you have to how you the three cases: deleting the leaf node, right, deleting the node with one child, and deleting the node with two child. Okay, but here there is one catch is there. After deletion you have to check you have to update the height of all the nodes. Okay, always we delete the leaf node. Okay, so then again you have to go to the parent and check its height. You have to update its height, whether its heights left child, max of left child and right child, and plus 1, that you have to do. So when you do that, the balance factor may change. If balance factor change, then you have to rotate. Okay, that deleting the AVL tree, deleting nodes in the AVL tree, I leave it as an assignment. Okay, or probably that will be the next lab assignment or whatever it may be. So you can start thinking on that lines, right? Thank you.